Hello, everyone. Good afternoon. I will quickly talk about our work on conflict replicated data types, Syriani and Constantin and Masson. We all know that we've been building these systems, and now we're building these systems, and these systems, the newer ones, obviously are showing a great deal of heterogeneity, complexity. So it's not a matter of one discipline building systems anymore. It's rather a collaboration of multiple disciplines. Here on the right side, you see typical cybercritical systems or software-intensive systems, as we call them nowadays. But of course, collaboration can be approached in many, many different ways. Typically offline, non-real-time are the ones shown and encountered in this domain. This is a big problem because, of course, when we talk about real-time, we already associate, real-time interactions with a better collaborative endeavor, and we all know Google Docs and similar products which allow you to collaborate in a real time. And the problem is, of course, that these sort of techniques are well known in programming. When you have linear structures such as text, you see VS Code, you see code with me from JetBrains, you see Datatypes for Atom right over here. But these techniques are not really used in model-driven engineering. This is the problem here. So what we've been working on is conflict replicated data types to provide real-time collaborative facilities for model-driven software engineering. And in this work, particularly, we looked into how can we make extensible conflict-free replicated data types. So just to give you, probably not everyone is familiar with the notion of conflict-free replicated data types. It's an emerging topic, but just to give you a taste of it, imagine this not so imaginary scenario where I'm sitting here and you're sitting here, and of course scattered all across the world. The distance between us is over 10,000 kilometers, and the thing is, this is a substantial thing from yesterday. Let's imagine that we're collaborating on a very simple example where you and me same variable x that's the same value at time to 0, and I decide to increment this value by 5. And I'll let you know this by sending you a message, hey, please update your variable. And you do so. Okay, so far so good. This is very trivial, but then I will decide at time step 2 that I want to further increase my variable and send you this message. However, because of the large thing between you and me and the distance and the particularities of the routing network between us, this message seems to be appearing arriving earlier than the first message. So when you look at the red side, well, it's very plausible to say, well, the last time I updated my value, the latest value of x20, whereas on the right side, the latest value is 15. Now, this is obviously not good. This is what we call inconsistency between the two sides. So, of course, we want to reject this, right? We want to commit to 20, but how do we do this? So the big problem here is, of course, that in a real-time setting, when you want to ensure real-time collaboration, there's no time to stop and just discuss, okay, should I go with 15 or should I go with 20? No, you need some mechanisms in place which will treat this implicitly as you go and resolve these conflicts, hence the name of this technique and the name of conflict-free replicated CRD. Sure. CRD/CR is Sound Algebraic Framework. And they come in 2 flavors. One of them is operation-based CRDTs, where the emphasis is on the dynamic nature of operations being and messages being exchanged. And as Sound Algebraic Framework, operation-based CRDTs demand that concurrent operations are committed. So, just to recap, obviously everyone knows it. This is the commutative nature of algebraic structures. So the order of messages doesn't matter. This is what we demand from operation-based CRDTs. And well, here's an example. If I write a paper and I do the relative work first, and then the intro is the same as the opposite order, I will arrive to the same result. And this is already enough. in many cases. This is the nice thing about CRP, that it's a very simple requirement here, but it will ensure, as you will see, a lot of benefits already, and ensure conflict-free collaboration between two parties. Another flavor of CRDT are state-based CRDT, which is sort of the jewel of the operation-based, and again, some tricks with algebra. Semi-lattice. Once you have semi-lattice of messages, it doesn't matter if you first receive message Y and then message Z, or the other way around. So this is just the theory behind it. How do you put it here? It is simpler than you might think first. All we need is what we call the last write to win paradigm. So if you extend your messages, these update messages to timestamp, suddenly on the right side here, you can reconstruct the intent of this left side here. So you don't only receive the numbers, but you also receive at what time was this update applied. And then you will see, of course, the last write was x equals 20, so you can safely reject x. And then you arrive to consistent state. This is very simple to see, and this is also very intuitive, right? Obviously, you don't do this in real settings. You don't use wall blocks and port blocks or something similar mechanism, but in essence, in principle, this is what you do. You leverage the fact that messages can be processed in an arbitrary order, and the order doesn't matter because they are commutative. Of course, the question is, how do you implement CRDTs, right? And you can do this in two ways. Either you say, well, I will implement it in my application, and conflict-free nature of message exchange. So I will receive the messages from other parties, and I will reconcile, and I will encode this in my application. Or this is what CRDT then we do. We say no. Let's push it deeper. Let's push it to the level of data types, and this means if you can ensure conflict-free, the conflict-free nature at the data level, you can build whatever applications on top of the data layer, and you will enjoy the benefits of conflict. Now, the problem is, of course, if you look in the literature, typical CRDT looks like this, right? This is not something you want to really work with. The implementational details, the complexity of implementing such a data structure is huge. It comes from Mark Shapiro and a company who worked first on CRDTs. So what we did in our work, of course, if you look at this also, Extensible is a challenge. So what we did in our work is we developed two frameworks. One of them is what we maintain as a production framework, and another one was a more experimental framework. We developed a handful of CRDTs, and we targeted model-driven engineering settings where graphs are the prevalent data structures and not text. So if you remember the first slide, we mentioned that collaborating over program code is fairly easy because you have text, right? Essentially, you could use a mechanism used by Google Docs, and you will have the same effect, right? Of course, you have to put into a nice IDE, but essentially this is what you get. But here, how do you ensure conflict-free nature between graphs, where you have all the invariants between edges and vertices? It's not trivial. So a framework called Loki is available open source here at this URL. What you can do with our CRDTs is the following. Let's imagine that you have you want to build a mind map, and I also want to build a mind map collaboratively with you. So your graphical representation tool here is built on our collaborative type system, which ensures conflict-free collaboration with my side. And I also use the same collaborative type system to build my textualization. So this is very simple. We can be distributed physically because we use Q and Q to coordinate between distributed replicas. And this is what we encoded here in our framework. All the communication, all the type system, and all you have to do is you have to take these simple Python types and stack them. On the bottom of our framework are these are the CRPs we use: graphs, maps, vertices, edges, and we built a sufficiently rich modeling layer on top of it. You might recognize these from now, EMF. All these frameworks built on the same principles of graphs. One trick we play here is that we use full objects here, which allows us to. So if I say I have a MindMap class in my application and the MindMap instance, of course, there's a linguistic conformance between these two. What I can do is I can say, well, but this MindMap object here physically conforms to the full object type, which is the persisted SNLWW vertex of a graph. Right? So then I will have a huge model which is consisted of vertices and edges. And of course, this MindMap box here, it's a class conceptually at this blue level, but at this level here is just another form. And if I look at these two objects and I look at the MindMap example, one of them plays the role of a class, another one plays the role of an object. At the end of the day, they're all just vertices in the graph. Of course, this edge here is an association, and this attribute here is natural. So this is how we work with our framework. We give all this to the low level here, conflict-free application. This middle layer here gives you what we call the physical meta model, gives you this graph semantics, which you can build your domain-specific application on top of. And everything that's related to conflict-free and collaboration is ensured here at this low level. Okay, as you see, it's very easy to use API. You can extend these types here, these white boxes with your blue domain-specific boxes. All it takes is just extending the class or the full object in domain-specific types, and actually the majority of these So what you see here is that that vertical extension is fairly easy to do, and then we ask the question, and this is what this paper is mostly about. How about horizontal? How about horizontal extension? Can I derive new CRDPs from existing CRDPs in an efficient way, so that I don't ruin the performance of my CRDP layer? Well, for that we with another proof of concept framework, just to experiment with the extension concept. For Polar server and available here. What we did is we implemented CRDP types in C++, so that we can observe the performance in great detail. And what we did was, it's a very simple example. You take an LW set and we built conflict-free maps out of registers, FTs in a conflict-free set, and we derive conflict-free graphs out of conflict-free maps, set, and so on, and so on, and so on. So you see, you can sophisticate your conflict-free types by just reducing previously defined conflict-free types. The performance is shown here, and this is what we were really interested in. We wanted to see a linear scale of the memory as the number of objects in the application increases. We did some synthetic studies here, so we built up an application by these principles, and we simulated a collaboration between 100,000 users with some price and these. And what you see here is that as the number of objects increase, the memory allocation, the memory this application took scale up linearly, which is exactly in line with the expected characteristics of CRDT. Of course, you don't build an application where CRDT without garbage collection. You need some smart management of memory. But the point being, what we showed here is that it's absolutely safe to safe ways to construct complex completely replicated data types from other replicated data types if you have access behind the API. This is a short paper, so we don't really have time to go into the details, and I hope it made sense what I just explained here. If you are more interested in our work, we have a recently accepted paper in Constantin, describes our framework, and we show how multi-level modeling can be supported by real-time replicated data types. Conflict-free replicated data types. One of our ongoing work is model language coevolution by multi-level real-time collaboration. We are working on this quite hard, and you may know the SNPM tool, which is a web-based multi-paradigm modeling tool, and we are re-architecting this modeling tool, new incarnation based on the framework. And just to wrap up, what you saw here is that indeed real-time collaboration is important, especially unlike heterogeneous systems. And one way to do this is by supporting real-time collaboration at the data level, and CRD are one mechanism for this. And the advances of the two different frameworks, Loki and the Polskie server. One of them ensures very trivial and easy customizability, vertical axis, and the other one horizontal axis. I think this is pretty much it from my end. I really try to speak loud, and I hope some of the next.
Thank you very much, Istvan. So now it's time for questions, and just my first comment or my impression that the problems that you mentioned at the beginning as a motivating part of your talk remind me on all typical problems that we also resolve at the level of database management systems. As concurrency control is the same problem, and you have also two options. One option is to have a centralized system and one DBMS server, and the other option, much more complex, if you have a distributed system and you have all those problems multiplicated back just because the system is distributed. So the same is with you. Have you used any analogies in resolving the problems at your level of DBMS mechanisms that they offer for similar situations?
Yeah, so if I understood the question correctly, yes, indeed. So for example, LWW, the paradigm itself, this paradigm actually comes from database management systems and distributed systems, indeed, and the mechanisms to treat the flops, the Lamport flop, of course, comes from the distributed systems. The big achievement of CRDT, and this is an emerging topic, the big achievement of CRDT is just to put this framework, this algebraic framework, on top of what has been done before in distributed systems and database management systems, and this is pretty much it. So some years ago, the prevailing paradigm for real-time collaboration was operational transformations, and this is what Google Docs, for example, implements nowadays still. But it has been shown that that well-developed and well-known techniques can be also applied for replicating text and graphs and very complex systems. But yeah, very good point. This is nothing new. What's below here? What's new is actually deriving these types and providing them as standalone types behind an API, and then you can use them to build software.
Yeah. In general, those are always very complex algorithms, not just in terms that we do not know what would be inside, but they typically need years to be developed at a level to be free of any defects.
Exactly. So this is why we embarked on this journey of developing these frameworks, because we see an emerging need for such mechanisms in the MD community. However, if you look at it, and this is just one excerpt from this paper, this is a fantastic paper where they list in 50 pages just algorithms, just data structures, and these are not things you really want to give, to someone to implement, but you need some predefined primitives and then composability, reusability, extensibility, so that you can build your applications in a more rapid fashion.
Perfect. Thank you very much.